In this video, I'm going to be working through the section 3.3 homework problems on web work. In section 3.3, we're looking at the connection between factors of a polynomial function and the x-intercepts or zeros of the function. So in this problem, we're asked to match the polynomial functions with one of the graphs below. So let's look at number 1. The function f of x equals x minus 1 times x minus 3 squared. Well, each factor determines one x-intercept. So if x minus 1 is a factor, then the number 1 is going to be an x-intercept. We've seen this several times when we set the function equal to 0 and set each factor equal to 0. So for number 1, if x minus 1 equals 0, then add 1 to both sides, you get an x-intercept at plus 1. We have x-intercept at plus 1, and notice that the exponent on the factor makes a difference about the behavior of the graph at that x-intercept. When you have only one factor of x minus 1, the function will look like a straight line at the x-intercept of plus 1. Now look at this factor, x minus 3, the quantity squared. We have two factors of x minus 3. So we see that the x-intercept is going to be plus 3, and the squaring makes the function act like a quadratic function, like a parabola near the x-intercept of 3. So we're looking for a function that has a single 0 at 1 and a double 0 at 3. So if we look up here, there is only one graph. There's two graphs that have x-intercepts at 1 and 3. And we look at the difference here. For graph B, the x-intercept at 1 looks like a straight line right at that point. So there's a single 0 here. And then at x equals 3, the graph looks kind of like a parabola. So that's a double 0 here at x equals 3. So we see that conversely, graph D has a double 0 at 1 and a single 0 at 3. So for the first function, this would be graph B. Now let's look at the other function. Look at number 4. We saw this would have an x-intercept at 1 and an x-intercept at 3 as well. Here's a double 0 at x equals 1 and a single 0 at x equals 3. So function 4 must be matched up with graph D. Now let's look at the function number 2. If x plus 1 is a factor, then negative 1 is going to be the x-intercept corresponding to this factor. So there's x plus 1, the quantity squared. So this function will have a double 0 at negative 1. And we have two graphs remaining, A and C. And we see that graph A has a double 0 at negative 1. The graph looks like a parabola at negative 1. And there's another single 0 at x equals positive 3. And that matches up with this factor right here. So function 2 is graph A. And by process of elimination, function 3 should be graph C. But let's just confirm. X minus 1 is a factor, so plus 1 is a single 0. X plus 3, the quantity squared, means that negative 3 is the x-intercept, but it's a double 0. So we have a quadratic behavior at a negative 3. And we got it correct. All right, let's move on to problem number 2. In this problem, we're asked to find a formula for the function f of x that's a cubic function, so it has degree 3 polynomial function, and it has 3 zeros. The zeros I'm given are negative 2, and 6. So each of these zeros determines one factor of the polynomial. But further, we have to have an equation for f of x where if we plug in 9 into the function, you should get 8 out. So let's work this out here. So for number 2, we're given 3 zeros, negative 2, and 6. And so each one of these zeros determines a factor of the polynomial function. So here is the expression, the general form of the function. We get a leading coefficient, which I'm going to call A, times the 3 factors that are given by the 3 zeros. If negative 2 is a factor, then I'm going to use x plus 2 for our factor. And so we have another x minus 2, so we have another factor of x plus 2. If 6 is a 0, then x minus 6 is a factor. So this is the general form. We need to figure out what the leading coefficient a is going to equal, and to do that we're going to use the fact that when I plug in 9 into the function, we should get 8 out. That is, f of 9 equals 8. So when I plug in 9 to this expression for x, we can set that expression equal to 8 and solve for a. So this is what it looks like. So when I plug in 9 for x, I get these expressions, set that equal to 8. And then we see that 9 plus 2 is 11, 9 plus 2 is 11, 9 minus 6 is 3. So 11 times 3 is 363. So I have 363 times a equals 8. Dividing both sides by 363 gives us a leading coefficient of 8 over 363. So I can plug this expression back into the original function. And here we have the final answer. The formula for f of x would have a leading coefficient of 8 over 363, and then times the three factors, x plus 2 times x minus 6. Alright, so back in web work, I'm going to enter my answer as 8 over 363. And then put the factors x plus 2, x plus 2, x minus 6. And I could have done x plus 2, the quantity squared, because I had the same 0, and we got it correct. Okay, now let's move on to problem number 3. All right, so for problem number 3, we have a degree 4 polynomial function, and we have that it can be factored into this form right here. So I'm not actually going to do the factorization to get the answer. We can just use the graph to do this. So if we look at the graph more carefully, we see that there are two x-intercepts at -1 and +1. So these are the values of R1 and R2 that are required in the expression of the factored form. Now, we see the difference between the shape of the graph. At -1, the graph crosses right over at -1. So it looks kind of like, if you zoomed in, it looked like a linear function right there. So this is a single 0 at -1. At +1, the graph is curling down, and then it switches to curling up like a cubic polynomial. And so there's actually a triple 0 at +1. So this means you would have a factor of x minus 1, but since it looks like a cubic polynomial here, it would be x minus 1, the quantity cubed. So on our expression here, the single 0, R1, is going to be at -1, and the triple 0 is going to be at +1. So I'd put in x minus -1 here, and then x minus 1 to the power p, and since it's a triple 0, I put p equals 3. And we get a correct answer. So we see that each factor is determined by an x-intercept, and then moreover, the shape of the graph at that determines if there's a power or the multiplicity of that x-intercept. Let's move on to number 4. All right, in number 4, we are given a polynomial function in factored form. We need to find the y-intercepts, the x-intercepts, and then solve the polynomial inequality when f of x is greater than 0 and f of x is less than 0. It says do not sketch the graph, but this is actually the best way to solve these inequalities would be to do a short sketch. So let's analyze this problem more carefully. All right, for number 4, we have the factored form of the function. And in order to find the y-intercept, we're going to set the x-coordinate equal to 0. So solve for f of 0. When we plug in 0 for x and these three factors, we get -5 times 4 times -3, which equals 60. But the directions say to enter our answers as a point. So we would enter the coordinates 0, 60 for our y-intercept. Now for our second part, we have to find the x-intercepts. To find the x-intercepts, you set this function equal to 0, and when we do that, then we can in turn set each factor equal to 0 and solve for our x-intercepts. And so we get 3 x-intercepts at 5, -4, and 3. And again, we have to write these as points. So we would enter our answers as 5, 0, -4, 0, and 3, 0. Part 3 asks us to solve the inequality f of x greater than 0. So we see that f of x, these are the y-coordinates of points on the graph. The y-coordinates will be greater than 0 when the graph is above the x-axis. So using what we have already discovered about the x-intercepts, we have x-intercepts at -4, 3, and 5, and this is a cubic polynomial which will go down to the left and up to the right. So the only way that this graph could hit these 3 x-intercepts is in this fashion right here. You can verify this with the graphing calculator or other graphing utilities. So recall, we're looking for when the function is above the x-axis. So we see that this occurs when x is between -4 and 3, or when x is greater than 5. And we're asked to write our solutions in interval notation. So x between -4 and 3 would look like this, parentheses, -4, 3, parentheses. Or we use a capital U in WebWork, so it's a union symbol. And then x greater than 5 would be parentheses 5, infinity. And we can type in INF for infinity. The last part of this question asks us to solve the inequality f of x less than 0. This is conversely when the graph is below the x-axis. Again, the y-coordinates will be negative, the y-coordinates will be less than 0, and the graph is below the x-axis. So from this graph, we see this occurs when x is less than -4, and when the x values are between 3 and 5, the graph will be below the x-axis. So x is less than -4, or x between 3 and 5. In the interval notation, this looks like -infinity to -4, union 3 to 5. So now back to WebWork. We enter our y-intercept as a point, 0, 60. We enter our x-intercepts as points, 5, 0, and we have to separate them with a comma, -4, 0, 3, 0. And we saw that the function was above the x-axis between -4 and 3, union 5 to infinity. So I write INF for infinity. And conversely, the function is below the x-axis from -infinity to -4, union 3 to 5. All right, we got the correct answers. Now let's move on to problem number 5. So in problem number 5, we're asked to solve 2 more polynomial inequalities and enter our answers in interval notation. So to solve problem A, we're going to set this trinomial, x squared plus 4x minus 5, we'll set that equal to a function f of x. And then we interpret this as determining when is the function less than or equal to 0. That means the same as when is the graph of this function below or on the x-axis. For part B, we'll set up a function and determine when is the function above the x-axis, because we're asking when is this polynomial greater than 0. Alright, so number 5, we're trying to solve the inequality x squared plus 4x minus 5 is less than or equal to 0. So we set our function f of x equal to this polynomial, and then we're going to determine when is this function below or on the x-axis to solve the inequality. So to first solve this inequality, I'm going to factor this trinomial. We see that this trinomial factors nicely because the binomials would have leading coefficients x and x, and I can find two integers that multiply to -5 and add to 4. That'd be +5 and -1. So from this factored form, we can find the x-intercepts from each one of these factors. X plus 5 gives us an x-intercept of -5. X minus 1 gives us an x-intercept of +1. So now we can analyze the graph of this quadratic function. We see that we're going to end up with a parabola that looks something like this. So we have an x-intercept at -5 and at +1, and this is a parabola that opens upward because we have a positive leading coefficient. So the graph looks like this, and we're just trying to determine when is the function less than or equal to 0. That would occur when x is between -5 and +1, including the x-intercepts -5 and +1. So we see that x is between -5 and 1 inclusive. In an interval notation, this would be written as bracket -5, comma 1 bracket. Now for part B, we have to solve a similar inequality. F of x equals 5x squared plus x plus 5. And we want to know, when is this function greater than 0? Well, if we use a graphing utility, like on a graphing calculator, we can enter this expression, and then when we graph it, we'll see that we'll get a parabola that comes down and actually never even touches the x-axis. This quadratic function comes down to height 5 and then goes back up. So this function is actually always above the x-axis. So if we're trying to find out what values of x makes 5x squared plus x plus 5 greater than 0, it turns out that every x and x value would make this true. So since f of x is always above the x-axis, the solution is going to be all values of x. And when we want to write this in interval notation, we would write this expression as parentheses -infinity to infinity, parentheses. So all real numbers satisfy this inequality. So back in web work, we saw that this function was less than or equal to 0 between -5 and 1, and we want to use square brackets here to include the endpoints. And when is this function greater than 0? We saw that this function was always greater than 0, so we enter all real numbers, or -infinity to infinity. Now let's see number 6. In number 6, we're asked to solve the following inequality. So again, I want to think of this in terms of a polynomial function. This function will be greater than 0 when the graph of this function is above the x-axis. So let me sketch a graph of this using Desmos. So here's a graph of the function f of x equals x minus 7 times x minus 18. We see from these factors we're going to get two x-intercepts at +7 and at +18. And we see that we're asked to figure out, when is this quantity greater than 0? Well, we can see from this parabola that the function is above the x-axis when x is less than 7 or when x is greater than 18. So this would be from -infinity to 7 and then from 18 to infinity. And we want to be strictly positive, so we'll have parentheses on our interval. So back in web work, I can enter this as parentheses -infinity to 7 union 18 to infinity. So this would be all real numbers less than 7 and all real numbers greater than 18. And we see we get a correct answer. Moving on to number 7. So for number 7, we have to solve another polynomial inequality and enter our answer in interval notation. So this expression is a little bit harder because it's not in a factored form, but we're going to use the same principles. We're going to set this equal to a function, And then the solution to this inequality will be when the graph of this function is below or on the x-axis, because we have an expression less than or equal to 0. All right, for number 7, we're trying to solve x cubed minus 16x is less than or equal to 0. So we set our function equal to this polynomial, x cubed minus 16x, and we're going to factor this polynomial to find the x-intercepts. So you notice that each term has a common factor of x. So my first step would be factoring out a greatest common factor of x. This would leave x squared from the first term and a minus 16 from the second term. Now the factor x squared minus 16 is still factorable. This is called the difference of two squares, x squared minus 4 squared. So x squared minus 16 can be factored further as x plus 4 times x minus 4. So now we have our function in factored form, and then each one of these three factors will give us an x-intercept. From the factor x, we get an x-intercept of 0. From x plus 4, we get an x-intercept of minus 4. And from x minus 4, we get an x-intercept of plus 4. So when we look at this function, we can put together a sketch of the graph now. We have three x-intercepts at -4, 0, and 4. A cubic polynomial with leading coefficient +1 would go down to the left and up to the right. So we get this nice cubic graph here to match up with the x-intercepts and the end behavior. And now we're trying to figure out, when is this function less than or equal to 0? In other words, when is the graph below or on the x-axis? So f of x is less than or equal to 0 when the graph is below or on the x-axis. And we see that when x is less than -4, the graph is below the x-axis. And we want to include -4. So x is less than or equal to -4. Those are solutions. And then the function is also below or on the x-axis when x is between 0 and 4 inclusive. So when we write our answer in interval notation, we get from -infinity to -4 inclusive, so we use a square bracket, union including 0 and 4, 0 to 4 inclusive with square brackets. So looking at this function in Desmos, we confirm the shape of the graph and confirm that the function is below the x-axis when x is less than or equal to -4 and between 0 and 4. So in web work, we see that x cubed minus 16x is less than or equal to 0 when x is between -infinity and -4 inclusive, union when x is between 0 and 4 inclusive. And we have the correct answer. So the final problem is very similar to this one. So in number 8, we have to solve another polynomial inequality, but notice that there's no 0 on one side of this inequality. So the first thing we're going to do is move all the terms over to one side and then use the same technique to determine when a graph is above or below the x-axis. All right, for number 8, we have x to the 4th is greater than 25x squared. So to use the same technique we've been doing using graphs of polynomial functions, I'm going to first subtract 25x squared from both sides so that I end up with a 0 on the right side. So now we have an inequality that we're going to set our function equal to this expression and then determine when is the function with this formula above the x-axis. That'll be the same as solving this inequality greater than 0. So we set up our function f of x equals x to the 4th minus 25x squared. So we're going to determine when is this function above the x-axis. In order to do that, we're going to find the x-intercepts by factoring this function. There's a greatest common factor of x squared in both terms, so I factor out an x squared, and I'm left with x squared from the first term and a minus 25 from the second term. This is a difference of squares, x squared minus 5 squared. so it factors as x plus 5 times x minus 5. And now we have a completely factored form. We can determine the three x-intercepts. From x squared equal to, and we set x squared equal to 0, we would get a solution x equals 0. X plus 5 gives us an x-intercept of minus 5, and we get another x-intercept of plus 5 from the last factor. So when we combine all these x-intercepts and the fact that this is a fourth degree polynomial, we see that this is going to be a W-shaped graph. We have three x-intercepts. We have a single 0 at -5. We have a double 0 at x equals 0, and then a single 0 at 5. And the tails will both point up. So here's the graph of f of x. And we see that the graph of the function is above the x-axis when x is less than -5 or when x is greater than 5. So the solutions to the original inequality will be these x values. And so in interval notation, we have from -infinity to -5 and union from 5 to infinity. So here is a sketch of the graph f of x equals x to the fourth minus 25x squared in Desmos.com. And we're just confirming we have the three x-intercepts, -5, 0, and at 5. And we see the graph is positive when x is less than -5 or greater than 5. So when we go back to web work, we enter our answer in interval notation as -infinity to -5, parentheses, union 5 to infinity. And we get the correct answer, and this concludes the section 3.3 homework.